All right, so what we're going to talk about today, we go into heat exchangers, heat transfer. From there, we'll jump into some of the selection details for whether it's heat exchangers, pumps, try to get everybody familiar. It's time to ask questions, or if there's anything that we missed or want to cover more of, we can cover that more towards the end. So we'll go from heat exchangers into heat exchanger selection, then to pumps, a little bit about pump selection, and then from there, talk a little bit about some of the other technologies around what we have in hydronics. So a bit about refrigerants and air to water units, a little bit of cogeneration, some of these different topics, how we've integrated some of these items, how their application, where we see them going, where they've been. So, all right, let's start off with heat exchangers. So within the heat exchangers, we'll first talk about different types of heat exchangers and methods of heat transfer. We're not going to get too deep into heat transfer equations, just some basic things that should be considered when you're making a selection. And some design examples, and then some examples of how we adjust those parameters, how they will impact our selections, and then end with some tips. So a heat exchanger, what is a heat exchanger? Clearly tell by the name, we're exchanging heat where the heat is going from warmer fluid to the cooler fluid. Sorry about that. Some of these, when you get this slide deck, there's plenty of slides I've blanked out. So if you want more detail on any of these items, for every slide, there's probably a couple that are hidden that you can search for reference later. Some more common heat exchangers that you're going to be working with in the commercial building services where that you already work with, for the most part, are covered by these three. There are other heat exchangers or forms of heat exchangers designs that vary from these. So, for instance, we look at that the middle one. We have our U-tube shell and tube heat exchanger. There are other shell and tube heat exchangers where rather than a U-tube that bend in the coil, we're going straight through. There's many different designs depending on what we're trying to transfer heat to. Other common ones on the far right-hand side, what you see our gasketed plate and frame heat exchanger. So it's our gasketed unit, sometimes referred to as a GPX. On the far left-hand side, we have our brazed plate heat exchanger. And once again, another plate type. So starting off with the shell and tube, what we have is we have here. I've got a different view than everybody. So we have fluid flowing on one side of the tubes. We have for the heat source side. For the cooler, we have on the other side. So whether we're water to water, we're steam to water. Shell and tube heat exchanger is probably the most broad application. There's a lot of flexibility in terms of the material type, the ability to manufacture the tube bundles versus the plates, configure them to order in terms of pressures or specific temperatures or applications with material type. There's just a lot more flexibility for really every manufacturer out there. Some of the limitations or disadvantage, though, of these types of units is that we don't recommend any further than any less than a 10-degree approach temperature. As we go further into this, we'll talk a bit more about the approach temperature and seems pretty clear as to why we wouldn't want to be below that the 10-degree minimum as recommended. We'd then shift to like a plate style heat exchanger. So plate and frame units, they're excellent in terms of their surface area, very thin wall units. If you look at the tube bundle of any of these copper units, great temperature cross. We'll get into temperature cross and temperature approach in a moment, but these are great for a small footprint. There are some limitations though in terms of material type. So you're going to have the obvious of titanium 304, 316, those ones, but beyond that, there are some limitations. And same with the brazed plates. There are options to have like a nickel brazing. If you have DI water or some special process that requires it. So, some of these advantages: temperature cross, the approach we'll talk about, and part of the benefit to this unit is the turbulence that it creates with the chevron patterns, and has a true countercurrent. So take that slide. We'll talk about in just a moment, actually. In terms of equations, the most basic would be the heat transfer equation of when George mentioned earlier, I think that a couple times in the presentation where we're doing the calculations, likely referring to primary, secondary, and the energy in and the energy out, where we were taking, let's say, 500 times the delta times the GPM, we were determining that load. It's really where this comes from. So if we take this and we say, let's say we use a specific gravity of 1 for water, 60 minutes times 8.34, it's just over 500. So that's why a lot of times we'll just use 500 as placeholder. But it's very important when it comes to, and something I'm going to mention a couple times in this, is that when we're creating schedules or we're doing anything where we're trying to determine what the load is or where we're transferring heat, we need to make sure that everything always balances. It's surprising, but a lot of times on schedules, they're not balanced. So just mentioning that, I'll mention a few times here, but this is just a basic one that you're already familiar with. We'll talk a bit more in a moment. Should probably unhide a few of the slides to talk a bit about the log mean temperature difference, but the log mean temperature difference, think of it as the further apart that the temperatures are as if you're on one side of the heat exchanger versus the other, you're going to have better transfer of energy. As they are closer in temperature or you reduce your surface area, your ability to transfer would be greatly diminished. On the right-hand side, what you can see is the countercurrent. And so that's very important with heat transferability, and we'll do an example of that coming up after the log mean example. But the countercurrent's important. And something also that we'll give a visual to is the temperature approach with the countercurrent flow. So where you have your hot in is on the same side, you have your cold out, and where you have your hot out, you have your cold in. That's going to give us our best heat transfer. And now a temperature cross, that's going to be when that cold water out is greater than your hot water out. Just to give a visual to it, I think this is much better. So when we think of our temperature cross, that's where, let's say, our cold out is greater than our hot out. That's where we have our temperature cross, and at the same time we have our approach, where our cold in, our cold out approaches our hot in, and our hot out approaches our cold in. So the greater our temperature difference, the larger approach. Just gives you the equation for the log mean temperature difference. I probably should have had a couple slides ago, but it starts to make sense as to the smaller the approach, the more surface area, the more difficult it is to transfer heat. The temperature cross, obviously, then your log mean temperature difference is going to shrink, and in shrinking also reduces your ability to transfer heat. And so this right here is an example where, for instance, if we have true countercurrent here. So if we have on the hot side, we have 95 degrees entering, and on the cold side, if we had 73 degrees entering, and then we have 82 out, 85 out. Taking the equation from the last page, what you can see here is that we have a log mean temperature difference of about 12.5 degrees. Now, if we compare that to if somebody were to incorrectly pipe the heat exchanger and we had co-current flow, then you will notice that our log mean temperature difference is reduced. Doesn't look like a significant amount, but what it amounts to is about 25% difference in heat transfer, less heat transfer. So it's important to maintain the best log mean temperature difference we can to maximize our use of the surface area. So when it comes to heat transfer equations, this one here, what we just wanted to show is that the surface area relative to the heat load and the heat transfer rate. So as we increase our heat transfer rate, the required surface area decreases. And then the same for the log mean temperature difference. As we increase our log mean temperature difference, then it would impact the surface area wouldn't be required as much. It'd be more impactful for that surface area. Let's see. When it comes to selections, so kind of going back to that heat balance equation, we need so many inputs to be able to fill in the blanks. And no matter what the software is that you use, it'll be the same case. So within our software, we ask for 5 of these 7 items, and then we can work into the others. So if we have the flow rate and on one side, and then the inlet outlet on both sides, then we know, okay, well, the load is X on this side. The load has to be the same on the other side, so we can figure out the flow rate. Also, the allowable pressure drop, materials, space restrictions. So there's certain considerations that we need to make. Similar later on, we'll talk a bit about some of the considerations with pumps, but with heat exchangers, the same thing. Today, for instance, we had height constraints in a room, but then also we had limited floor space. So it's trying to figure out the balance of the smaller we make that approach temperature could potentially make us have a really tall unit. So then we say, okay, well, if we're going to have a really tall unit, that unit may have a very large frame, and that frame may not be able to be reduced. So we made a slight adjustment to the approach temperature, which made it so that we could reduce our surface area and how tall the unit was, which reduced our frame size. So, there was one selection we had, but then, as these different variables got piled on, it became to the third revision of it. But it's nice to have those details when we can at the start. Let's see. So here's just a quick example of, let's say we have our chilled water and our tower, that both of these down below, what we're showing is that, let's say we take this, put it in the heat balance equation, we're at 2.4 million. It's important we do that. Surprisingly, it's very, very common that these numbers don't necessarily work out. So just putting it out there so that nobody gets a silly call, or somebody doesn't call you and somebody just makes a selection that they should have called you about. Here's something that will pop up in a lot of the different softwares, is that as you it'll give you a bit of a visualization of this temperature cross. And so in this case, what do we do here? Okay, so this is the given situation where we have the existing approach temperature. We look at the difference between the 57.8 and the 54.2 versus the 53 and the 51. Between the 53 and the 51 give us a 2-degree approach. Now, if we were to increase the approach to a 3-degree and a 2-degree, let's see here. Sorry. I shuffled the slide deck right before here. Let's see, here we go. Go back. So here we go. Right, so in this case, we have a we have the 3.6 degree and the 2-degree approach temperatures. That gives us a log mean temperature difference of 2.7. So knowing that the plane frame heat exchanger is recommended to a minimum of a 2-degree approach, and a shell and tube heat exchanger is recommended to not be any less than a 10-degree approach. If you were to have the situation where you required that 3.6 and the 2-degree approach, what kind of heat exchanger would you select? A plate style, right? I mean, it would be far from what you'd be able to select for a shell and tube. So we have that. And then, let's see. Plate style. So I had some of these set up where if you click at different things that pop up. In this case, what I wanted to show was just that, here we go. Cold, and then, all right. So if we have if we start with a heat transfer coefficient of 964, and we put it into the calculate using the equation for the area, and let's say we have 915 feet. Well, if we were to increase the heat transfer coefficient, where before we were talking about U compared to A, as heat transfer coefficient goes up, less surface area is required for the same heat transfer. So if we were, for instance, to allow for a greater pressure drop, so in this case where we have, say, 10 feet ahead or 10 psi in this case, that if we were to increase it and have an allowable pressure drop of 15, and so it would allow for likely create a higher heat transfer coefficient, and doing so would then be able to drop our surface area. So if we did that, let's say if we were able to increase it by 5 psi for the acceptable pressure drop, and our heat transfer coefficient now is 1105, then plugging into the equation then provides us with an area reduction. I believe that was about 200 square feet, and a price reduction to about 0.93, the original cost. A lot of times in the different softwares, we'll have the relative price where the least expensive component may be set at a 1, and then from there, you'll see like a 1.1, 1.2 relative to that base price. So you wouldn't see that with the software. So the next would be, for instance, if we were to take the tower water and we were to take that leaving water temperature of 54.2, and we were to elevate that return water temperature and allow it to return at 55.8 degrees, it would impact our flow rate. So our flow rate, to balance out to have the same heat transfer, would then be dropped to 1,000 gallons a minute. Now the 1,000 gallons a minute, it would obviously be a savings in the fact that we have the reduction of the flow rate. But what we also need to consider is that now we are reducing our LMTD, and reducing our LMTD is going to increase the surface area. So you're now up to 1.2 versus 1. So it kind of went the other way around from what we had before with the heat transfer rate. Exciting stuff. I figured I'd get this away now versus at 6:30. So the other stuff should be a lot easier, or a little bit more comfortable with everyone. So when we get into the software, there's depending on the type of heat exchanger, you have the ability to be able to select not just the type of the heat exchanger, but also what does it apply to? You know, is this an industrial item? Is this is it an AHRI 400 item? Is this going to be, is this a water side economizer? Does this have to be whatever it may be? And more frequently discussed, you have your AHRI standard 400 is very common. So I just wanted to, before I get into the software, it's tough not to jump from the software to this and back and forth. But so with ASHRAE 90.1, they require that waterside economizer be AHRI, but also has additional standards. And I'll show you in the software in a moment. But introduction just to AHRI and who AHRI is. So AHRI is a trade association. So hundreds of manufacturers, they come together, and essentially everybody's contributing to creating practices for testing equipment. Anyone can claim they have certain efficiencies, unless we all band together and say, all right, well, let's create a standard and let's have a third party test it. If not, then we're really not comparing equivalent products. So if anyone right now is already reviewing specs or has any familiarity with the HRI, it's very well adopted across the industry. Now with AHRI, they have a standard, it's standard 400, where, for instance, if you're in a selection software and a company is a participating member, you're going to see the option to be able to select AHRI 400. AHRI 400 is essentially just saying that that heat exchanger was tested in accordance to AHRI 400, which means that every year there has to be a sample of all different versions of those heat exchangers from whatever participating manufacturer you have is pulled, tested third party, and verified. Um, so it's just trying to make apples to apples in the industry, make everything comparable. There's others for different products out there. So with pumps, you have Hydraulic Institute, CTI for cooling towers, chillers, AHRI, and spoke with the folks at AHRI. They're expanding to not just the chillers, they're developing a standard for a product we'll be talking about in a little bit, which is a heat pump chiller. The 550, 590 that applies to chillers doesn't necessarily encompass the heat pump portion. So HRI's coverage of new products is continuing to expand. For a UL certification. Yeah, I guess it would depend on the product. Sometimes they'll also have the overlapping of different agencies. I guess we'd have to figure the specific product. And then like so the question was like what about UL compared to AHRI, HI? Just for reason here. A lot of times there'll be overlapping agencies, and certain agencies will kind of be the authority on whatever subject it may be. So like for instance, some standards, UL a lot of times would be like the safety aspect. But like for right now, for instance, I'm working with so ASHRAE, 15, the safe handling of refrigerants. They're working on a section for revising the charge limit for A2L, A3 refrigerants, and there's an addendum going out where they're looking to raise it for 290. I'll get to that. Actually, I'm jumping ahead of myself, but after ASHRAE releases their recommendations and so on, then you'll have UL. They've got like their 6033 like 2. There's a bunch of dashes they'll review, and then on top of that you have the EPA, and I guess it would have to be depending on the specific product. Each product almost has its own process, and then each one has maybe more of an authority of what listing is most has become the standard for that. But yeah, I can, and then during the break, dig into that one a bit more. So just while we're on this one though, anyone that is an HRI member, which there's quite a few, most of brands are familiar with, or likely HRI members, is they have an item called a certify all provision. So what they want to make sure that doesn't happen is that, let's say we're a participating member, that we don't go out there and an HRI 400 heat exchanger has a slightly higher cost because it has to pay for the listing. So for instance, if someone were to sell something that was rated for industrial and didn't do an HRI 400 standard, well then that would be at a lower cost. It could potentially be the same exact heat exchanger, but it's not tested to that same standard. With the HRI certify all is that if it's a manufacturer that's participating, that they want to make sure that people aren't going out there and maybe trying to lowball a project and getting something that's not HRI 400, that they want to make it so that if you're an HRI 400 member, HRI member, that you certify all of yours if they applies to primarily heating and cooling a building. So if you're using it for a process plant at Lint or something like that, for some food application, that might be one thing, versus if it were for heating or cooling of this building, then it would have to be 400. I don't want to beat this up too much. Just a couple items is that if there's glycol in it, it doesn't apply. It doesn't have to be the HRI 400. A couple other things. This slide is a bit backwards in how it explains it, but the unit, if it's a gasketed unit, if it uses water, salt water, and any reasonable capacity, it would be included. Let's see. And then how they define it is really just if it's primarily heating or cooling a building. If it's 50-50, then they side with that it is its primary purpose, and in that case, it would have to be the HRI 400. This here is just a couple slides just recommending that that the HRI 400 standard 400 is part of a spec, just so that people know that what they're getting is being third-party verified. And that so some manufacturers might put tested in accordance versus saying that they're tested too. And that's a big thing where, and that's fine. I think when a listing hasn't been established. So like what I was saying with like heat pump chillers, for instance, people might use 550, 590, that's for the chillers. They'll say test in accordance. If you look at all the manufacturers, they'll say test in accordance, but that's because there isn't one specifically for it because it has a heat portion. So the best that everybody can do, to be honest, is to at least test the chiller portion to it. But if there is a standard out there that is third-party verified that a bunch of manufacturers have joined, then it does make sense to list this as a requirement rather than, in accordance if something hadn't been established. Okay, yeah, so it was some time ago that that became the case. I'm going to switch my screen. We'll open the software here. All right, George, what do we have there? Okay, you can see system-wise, but here in the classroom, it says selections and submittals. Maybe go into the screen portion again. Sorry, everyone that's remote. We had some trouble before. Let's try this. That didn't work. Yeah. That has it listed on a different screen. I'm gonna have to pull up those settings again. Okay. Oh, worked. I had to do the same things before. Duplicate. Okay, keep changes. All right, now it's working here. Okay, so this is just wanted to do a quick example. And, I'm not going to harp too much on this. Most of it, when it comes to these softwares, you're just going to want to figure out yourself. Most of they're all pretty intuitive. No matter what brand everyone uses, they've all been out for so many years that they should be pretty intuitive at least. So in this case, what we have is this is Bell & Gossett. Bell & Gossett's ESP system-wise. So just a quick run through. Yeah, that'd be good. All right, so on the left-hand side, see if we can see it here. All right, so on the left-hand side, I'm zooming in pretty far for a little remote, but that's for the folks in the classroom so everybody can see it. So on the far left-hand side, you have these different tabs. So pumps, suction diffusers, triple duty valves, air separators, expansion tanks, heat exchangers, pickbees. It's quite a bit along here. So without exploring all of it right now, what I just wanted to do is continue our conversation about heat exchangers. All right, so selected heat exchangers, open ESP thermal. Say begin using ESP thermal. Now this is where we select our gasketed plate and frame heat exchanger. We have the details here on the AHRI 400 standard. So let's say if we were supporting heating and cooling or cooling in a building, then we would then have that selected.
See that more that breadcrumbs.
What was it?
The black bar, the black bar at the top more.
Oh, okay, yeah. Oh, yeah. Hide names, editors, hide floating meeting controls. Awesome. Thanks, George. Thanks, everybody. All right, so in this case, we have our gasketed plane frame heat exchanger. We're selecting one for heating and cooling, so we're going with the HRI standard 400. Now, This is where I mentioned before about how we just need to have 5 of those 7 conditions, and then some of the other ones may be helpful for preferences on the selection. So let's say, for instance, if we were to say, okay, we could adjust it and have our 10 feet ahead. It's another item probably should have noted to get back to presentation, but very common to see in the schedules is when somebody says somebody has 10 or 15, they mean feet ahead, but the software, but it might say PSI and very different things. So always paying attention to whether we're feet ahead or PSI. So let's say if we had 180-degree water and we were allowing it to cool to 160-degree water, and if we were to have, say we were operating at a low temperature application, let's say we had 100 in and we had 120 out. Now we can have it so that we can either put in the load, and we can say that we want, let's say 500 MVH. And doing that, we can allow everything else to float, or we can unselect that, put in, let's say 50 gallons a minute. Either way, when you do that, it'll pop up with an error if you don't. This right here just gives that visual that we were looking at before when it came to the approach and temperature cross details. So a little rundown on it. So we've got our fluid. So this is where you put in, if you have propylene glycol, be able to make a selection. How do I do this here? There we go. Try that again. All right. So if you were to change your propylene glycol or water, whatever you may have, it's pretty intuitive. You could also rate heat exchangers. So if you know what heat exchanger you have, you can put in some conditions, and then you can select the heat exchanger you have on site. And you can see whether, if it were new, how those how capable it would be of achieving whatever proposed performance you may have. This is here where we're able to make our selections for additional details. So whether we're picking our material type, our plate thickness, commonly 0.4, as you see, it starts eliminating certain models versus if we were to just go with a default. But additional capacity, single pass only, recommend single pass only for any of these units. When you start seeing the multi-pass on any of the plate frame units, you're going to see the connections often on 2 different sides of the plate frame. And if somebody goes in to service it, they're not going to be happy. It's going to be making it quite difficult. So if you could avoid it, I'd recommend that. So just gives a little bit of detail there. You'd also be able to pick double wall. Let's say if you have an application that would require it. And depending on the area too, so like what the codes are here versus other places, they could be quite different. So just make sure that we are selecting double wall where appropriate. So let's say if we were to select the first one. So the first one is likely going to be the lowest cost unit, but also make sure that it meets all the criteria. It's often how it funnels it. It's how well it meets those items. So if we were to look at it and we said, okay, well, let's confirm dimensions. We can then say, select the unit, select dimensions, and you can read through. So if you have a restriction here where, let's say you wanted it to be, so in this case, this unit has a frame depth of about just shy of 16 inches, and it's about 22 inches tall versus, well, these are small units, so you're not going to have any constraints with that, but just as example. So then from there, you can select different material types. So whether you wanted to have different nozzle types, you select your other details like any frame or coating. Those are far less frequent. I'm just going to rush through this to this point. So at this point, if you needed any sort of 3D models, we hit save. More commonly, depending on how early we are in the design, we can usually leave things at this point. So what I select is PDF. This is usually what we're looking for. So we're looking for the printout. It tells us the conditions in which it was selected, it would operate, and then also the construction of the unit. So here you have your HRI certification down there. We just want to show that for a moment in the software, and then did it switch back, George, for people there?
Yeah, it's showing that exact screen at the moment.
It is?
Yeah.
Okay, good. see if I can. Trying to get full screen here. Let me see. Is it presenter view? Or do I have a high presenter view? How's that? Okay. So this is what you'd have emailed to you. Might not be something that it's not something that would pop up immediately, but it would show up in your email. Now, I just have this slide here just for considerations where once your approach temperature, once you approach that 2-degree approach, your surface area gets exponentially greater. And seeing people try to do even tighter approach temperatures, but once you're beyond 2, you have to start thinking about like how is this even going to be in the field? How can you even verify this is accurate? And all these units, they're tested in lab condition, and so often you go to these sites and we have all these different measuring tools on the heat exchangers for a specific application, but there are fittings right before that we're reading pressures, or you have to take considerations to making sure that if you are going to have an application that is highly sensitive, that you have that we have recommendations for straight pipe depending on what the item is. You just want to make sure that you have uniform flow. You don't have any sort of turbulence or distortions that would cause or impair any sort of the readings, but far less likely than okay. So we hide this. Is the bar still up there? Okay. More side panel. I did. Sorry, guys. Show. All right. Is that what it is? Loading meeting controls. Oh, sorry about that. Okay, cool. All right. So just some of the things that have been mentioned a bit, though, is just making sure that the measurement when it comes to feet of head on the schedule versus PSI, that the heat load, the load must balance, account for the fluid properties. So whether it's glycol, whether it's water, and let's see, the lower the LMTD typically results in the larger heat exchanger. So factoring that in, if you have space constraints, or depending on how you start weighing out what you need the performance to be versus what the site is able to support. And there's different ways where sometimes we can also adjust by maybe having, if we have height constraints, maybe we say, okay, we'll have multiple units in series or units in parallel. So there are plenty of other ways beyond just adjusting your conditions. You can achieve those conditions often. Just something that would require more conversation. I think that's good for heat exchangers. Now, with going into pumps, similar to heat exchangers, there are different considerations. So, sorry, I thought this was our swing order pumps. So now we're just jumping to system-wide. So with the system-wide selection, as I scroll down on the left side of the tab, all we were showing is that you can support pumps, air separators, expansion tanks, heat exchangers. So all of those items on the left-hand side, those are the tabs that we just saw. And we can generate any of those necessary files for the project. Now that we've already gone through the heat exchanger portion, figured what we could do is we could take a moment to make a few pump selections. So with a pump selection, similar to heat exchangers, there are different priorities, and so as a project designer or possibly the building owner, there's all these different considerations that need to be factored. So, obviously there's an impact from the first cost, the ease of serviceability, ease of access, floor space, whether the supplier is a supplier that maybe sells, direct to a contractor and may not have inventory for parts versus, some folks in the industry, including ourselves, we sell through wholesalers. So all the supply houses, they stock everything. So just how are you supplying it? And then also looking at the pump's life expectancy. So when we were, I think it might have been the first class, we pulled up the slide about the DOE where you have the life expectancy based off of the RPM, whether it's an inline, whether it's a base mounted. So all of these items must be factored when we're making a selection. And then also the best efficiency point, whether it's left or right of the best efficiency point. And then what the true operating cost and the system efficiency is, how that's going to integrate with the other products. So just as a point of reference, there's ASHRAE and HRI have their own regions that they recommend. Now with ASHRAE, what they do is they have their satisfactory pump selection region, and that's it's pretty flexible at 66 to 115% versus 85 to 105 for the preferred region. So it's actually HI, so Hydraulic Institute. You may see Hydraulic Institute more when people are talking about pump efficiencies. Hydraulic Institute plays a big role. So now, if anyone's starting to see pumps that they're coming with labels shipping on that say, pump efficiency index, they'll say PEI or they'll say ER. The DOE is requiring that a lot of these base-mounted pumps, or many base-mounted inline pumps in the commercial market these days, come with those ratings. HI is a big part of that, and developed the ER. So HI, they have their own region, and their region is at 70% to 120% of BEP. And just kind of going back here. So in this case, we have our BEP on the far right side of that green region. That's the 100%. And the preferred being 15% less or five over. And I think that a lot of times the concern has always been that if we select something to the right of the best efficiency point, the concern often is that there's so often we factor in additional head as some sort of a safety factor that the pump's really just going to fall off the end of the curve, which there are plenty of disadvantages to a head selection being exaggerated. We'll get into that in a bit, but I think in a moment we'll talk a little bit about how some of these efficiencies with variable speeds will impact where you want to be in this preferred region. There's HIs again. This right here is a good slide to be able to reference in the future. And so operation well below BEP to left, you very well could experience the low efficiencies, large radial forces acting on the shaft. Potentially, if you're riding far enough back, some cavitation. More likely, when you're going to see cavitation is when you start riding out towards the end of your curve. Your NPSHR is going to increase, and in doing so, that's when it may sound like they're pumping marbles, and some of these sites, maybe, I guess, without getting into that. So then to the right, I mentioned the NPSHR, excessive bending in the shaft, and the noise would be part of the cavitation, the vibration. When it comes to the selections, when we get into the software, one of the items that I like to pay attention to, so obviously we're looking at that duty point efficiency, but we have to keep in mind is that duty point efficiency is for our greatest load. So that's our design day condition. We have to also consider is that how infrequently are we really going to be operating at those conditions? Pretty rarely. And so I think something that's a bit more true in terms of what you will see for efficiency is a weighted efficiency. And you'll see this sort of weighting done on other equipment out there than just pumps. It's pretty common, but looking at the PLEV is quite important. So if we weight that 100% is of operation is at 1% of the time, then 42 for 75 and 45 for 50, then it gives us I think a more realistic efficiency rather than just selecting something on the duty point. Now all of those items I mentioned before actually are all items that will appear when you're in. I would imagine just about anyone's selection software. And you notice down at the bottom that 550, 590, that's the chiller rating for HRI. They do something very similar. And just giving a visual to the profile. So if we look at this load profile and we imagine operating all the time, it wouldn't be true in terms of our efficiency. So from here, I just want to jump into the software and take a look little bit about what items to consider when we're making a selection. Okay, so probably should have just put all of this into the slide deck. I believe it's this one. So then from here, okay, does that pop up, George?
Yes.
Okay, excellent. Okay, great. So let's say, for instance, we select pumps. Okay, people can see that. Or if there's a way to make the screen so that the letters are darker with a zooming item, but okay. So if we were to do just, let's say, a traditional selection, George did if you got a little bit about into the Hydrovar X series. What I'm gonna do is I'm gonna select an E1510. So an E1510 is a base mounted end section unit, pretty standard in the industry. That design's been around for a long time. They made some revisions to it probably in the last 10 years. And I think that even with all the new CFD software, they were barely able to improve any efficiency from the stuff that was done by hand many years ago. A lot of the upgrades actually came from material enhancements. So just like this one, just because it allows us to look at some of these ratings that we were just talking about. If we start looking at, let's say, this product, the replacement product that has the onboard drive, the trouble with that is that the software is only factoring the hydraulic efficiency, and it doesn't factor any of the motor details. So if you're comparing a unit that includes motor details and one that does include motor details, they could be a bit skewed, but I'll show you that too, I guess. So if we were to just run a basic selection where we said, okay, it's a E1510, it's a variable speed selection, censored, flow rate 350, head 50 feet, single unit, non-parallel. Maintain the standard motor details. The standard is non-overloading, so that no matter wherever you are in the curve, you're not overloading your motor. And let's just say that 68-degree water. Keep it simple here. All right. Now, there's plenty of stuff that pops up here, and this is all adjustable. So I have my own settings that I prefer, but if there are other ones that you're looking to select, whether it's the floor space or you're working off the PEI, ER at constant load, variable load, maybe you're looking at the NPSHR. So whatever the application and you're looking for, you can make those adjustments. So I have quite a few here, but in this case, for instance, if we were to say, take a look at our duty point efficiency. So the unit with the highest duty point efficiency is 78.9. And in terms of PLEV, it's also the same unit. So then looking at this unit, and we find our best efficiency point here is at this RPM would be at 80 gallons a minute relative to, sorry, not 80 gallons a minute, 80% efficiency at about, what's that, 475. Go back. Yeah, so that one, this unit, here we go. Is that better to see? Okay. So in this case, we have a unit selected where our best efficiency point is slightly to the right. This is a flatter curve. Also factoring in, if you have, let's say, a sensorless control, or if you even have censored, but the sensors are on the unit, just consider some of these curves that are quite flat where maybe the difference between even, 2 PSI could be the difference of several hundred gallons a minute. Just be a bit hesitant. So as you start looking at any of the sensorless units, they're all basing it off of like motor current. And so they know their RPM, they know the motor current. And without getting too far into it, is that you can have points where the controls aren't sure whether they're at one or another. So if I have anything where I've got a sensorless device that's based off of motor current, or I have some sort of critical application, there's what I would typically avoid is sensors directly on the unit with a flat curve. Ideally, it should work, but in the field, what really does happen is you could have fouling of those sensors. You could have many different things going on that can impact its what it things believe they're operating at. So if we were to make a selection here, we could then go with an overview of the product. We could do a cost comparison of versus if you were to have a constant speed, whether it's variable speed sensorless, whether it had just a whether it had remote transducers or units on it, or there's a lot to unpack here and to discover. But what I just wanted to show is that all of those items that are important for making a decision, I think really that's part of configuring your own profile or tailoring it to whatever project you're working on. Probably the downside of what I have here is there's a lot going on. So let's see. So just a little bit more about this. I don't know how well everybody can see it here as well as we can see it on the computer, but if we were to have an air separator and we were to have that 350 gallons a minute imported, we could then make a selection for our roller troll. Select the unit. We select the air vent, the details, add it to the schedule, just cancel that out. Or expansion tank. Sorry. If we were to make a selection, let's say there's HVAC selection, 40-degree fill. Let's call it at 190-degree water. Say tank fill pressure. Let's call it 12 psi. Let's call it leaf pressure 23 pounds. System volume 200 gallons. Just as an example. And then what I like is that it'll give you a selection for a single unit, but sometimes as we start working on larger projects, you may have some difficulty with units fitting through standard doorway or even replacements, where it's nice to just have a quick visual and say, okay, here's a calc sheet that'll provide showing that 2 of these smaller units will satisfy 1 of these larger, or possibly 3, or however far you want to go into it. So I think with the software, rather than watching me do any of this, I'm sure over the years, everybody's going to develop their preference. So what I'm going to switch to now is, all right. So I think that for the most part, we covered more of the basic components, the selection software, basic heat exchanger selections. And then from there, what I wanted to spend a little bit of time on is really talking about some of where things have gone, where things are going. Anyone that works on the plumbing side, I'm not sure any in the class, any who works on the plumbing side, I know Maddie does. Okay, it's a little bit of experience with that, and we see a lot of things come full circle. Where I was just talking earlier in the class, and might as well put a slide up here. Where's that control now? You see on your screen, George, for
system wise at the moment.
doesn't even show that Zoom is open, does it? Did I log out? Okay. Share. All right. Is that on there?
Yeah.
Okay. So a little bit about just a lot of things in the industry coming full circle. And in recent years, Maddie and I were talking earlier about, for instance, when it comes to some of the domestic water applications where, you might see some of these buildings pull out a 2,000-gallon storage tank, and you might have something as small as like a 12 kW element supporting that 2,000-gallon tank. And I mean, that's really just off of, to be able to satisfy a load, you have the volume or you have the generation. And in recent years, we shifted away from having volume because of the thermal losses, and we went into instantaneous units. And well, just a few years ago, you'd see some of these large IntelliHot units at a couple million BTUs an hour, rather than having storage tank, the instantaneous route. And then now people are switching to heat pumps, and the cost of these units can be 7 to 10 times the same generation comparable unit easily for the cost. And so what people are doing is they're saying, okay, well, I'm going to then increase my storage and decrease my generation, so that because the generation item, the heat pump, is the most expensive component. So if I can drop the size of the heat pump, increase the storage, it's pretty cost effective to be able to satisfy your project. And you're seeing a lot of high volume. So anyone that's working on these heat pump projects, you're going to see people kind of shifting to the old philosophy of that high volume load.
Studies or guides or literature that talks about the various, like maybe, base, fossil, and efficient, then high efficiency, then electric, and then
Like just the evolution of it.
yeah.
I don't have any document about the evolution of I guess the water heating design. I mean, some people, I mean, it really depends on the territory too, I guess. I'm just up here where it's difficult here in Massachusetts, where we're typically on the forefront for much of the country. So some of the things we're talking about, it's probably not a conversation.
Elsewhere,
Yeah,
Florida.
yeah, Florida, Texas, you're not gonna have these same conversations. And
Yeah.
so like this product, just as an example of that. So this is a micro cogen. Produces 24 kW, and it produces about 160,000 BTUs an hour. This is a product we picked up maybe in 2018 or so, George.
Yeah.
And what I like to bring this up as an example is because you go to a lot of these housing authorities, and I've installed these in many housing authorities around Massachusetts and Rhode Island, and you'll see 500, 600,000 BTU of water heaters. You'll have two of them, and you'll have all of the storage. And when you do the calculations out, and and also you can look at some of the load profiles if you're lucky enough to have that information. Usually not, but often what we would do is I've got several projects where I've got 160 MBH unit supporting 200 plus unit apartment buildings. And there are 500,000 BTU units are never kicking on. And when calculating out, it's like, okay, well, I can add another 200 gallon tank, and they should never kick on. But so often, many of these systems are so large, and you start thinking about the instantaneous philosophy. Like we sell a lot of like combi units. Combi units have taken over the industry to doing domestic water and space heating. For space heating, you really don't need that large of a load for a typical house, right? Like maybe 100,000 BTUs, 80,000 BTUs. That's probably good for most 2,000, maybe 3,000 square foot homes with modern construction. But the thing is if you have, let's say, two showers, or you have a reasonable domestic load, it's very, very common that people would put in a 200,000 BTU combi. So it's probably one of the most common sizes that you'll see out there, or for an instantaneous unit, 200,000 unit, where you start thinking about, okay, if I'm instantaneous versus if I do storage, seems silly, but to be able to have something that's 20% less output and be able to support 200 units. So just something to kind of think is a bit fascinating with how things are developed. Now, when it came to thought it was a slide deck. I was trying to go back here. So do a full screen. Yes, whatever. Just a little bit about a cogen. I mean, for the most part, so our unit is a natural gas unit, so it's not something that is really going to be selling in Massachusetts, but just trying to bring the idea out there, because a lot of folks, they may have be working off of biogas or renewable natural gas, or and there's certain things people are supposed to say or not say these days, but yeah, there's quite a few of these plants around the region, and they are quite beneficial. You start thinking about, I had ISO New England pulled up. It was easier to switch back and forth and show it, but you look at the grid composition and where our power is coming from, and you start factoring in the thermal losses from the station, the distribution losses. we've got an electric water heater and we're at almost about 100% efficiency on just a resistive unit. You have to think that that's about 100% of potentially 30%. And that's why heat pumps, there's such a good reason for many heat pumps out there. So this slide just represents is that, let's say you have your losses from your power plant. I don't think that wouldn't be factoring in distribution losses, because I think we're probably closer to like 25%, at least in this region. But you have your thermal losses through the plant, your distribution losses. Boilers typically would have a 10% loss, versus these cogen, they have the same input. Let's say natural gas, or many of the other brands, they may have renewable options, but you're at 93%. You're using your thermal and your electrical output. So it made a lot of sense. I spent a lot of time for a couple of years promoting it, because I was under the impression of, okay, well, if our grid infrastructure has difficulty supporting what we're doing now, and we're abandoning the gas distribution network, then why don't we make it so we repurpose the gas by doing this, and also, decentralized power generation. So there was a big push on that, and worked with the utilities. We created some incentive programs, and then when the 3-year plan came out, there was a big pivot away from this, but there's still opportunities out there. And the reason I mention it is because there's still a lot of opportunities. And I think it's going to play a big part of the future for any RNG or a biogas applications. I think the incentives are going to be pretty exciting for anyone that's involved in that. I just want to show here is that if somebody does become familiar with does encounter these sorts of projects, it's very common is base loading. So on the left-hand side, we have the lighter yellow. That lighter yellow is what would be produced by, let's say, a given cogen unit. And this just shows our electrical load adjusting. And, you wouldn't want to have a unit kicking on and off. These units, just like every other piece of modern technology, are quite expensive. So it's often best to maybe just have them base load, don't oversize, overpay, create more service from cycles. Those are the characteristics of ours. There's a bunch of them out there. This is one of our sites, and just showing how really did, so you can get excited about our piping diagrams. Oops. Let me do the full screen. Is it F11 here? So I don't have that. High floating controls. So, we're gonna have similar operation for heat pump chillers. So, in this case, the only way to create a return for a lot of these more modern technologies, when we're incorporating them into the systems, which a lot of times people are doing, because a 100% approach to some of these more expensive technologies can be so costly that they prevent the projects from moving forward. So you start seeing hybrid approaches. In this case, obviously, this isn't so much hybrid because they're both gas products. But let's say if this were, a high temperature heat pump of some sort, what we would do is we would stage equipment. That's the best way to kind of get the best of both worlds. Where, for instance, if your backup or your secondary is only running for 25% of the time, is there really any financial justification for maybe going the route of doubling your equipment? So a lot of times you'll see this hybrid approach. In this case, with cogen, the best payback, the only way really for payback is through runtime. So if the unit's not running as often as possible, you're missing opportunity at producing power, but you have to always make sure that you have a thermal demand. So in this one, I just wanted to
walk me through
yeah. So in this case, for this equipment, all the equipment's slightly different, but I think quite similar. So in this case, what you have is you have the cogen unit circulating a hot fluid to and from this panel. This panel is then circulating it to and from the storage tank, and that's really all that the cogen knows. The cogen knows that this tank is, yeah. So there's a heat exchanger in here with a circulator that's circulating between these two circuits. So that's really just isolating, keeping this circuit nice and clean, while this may be influenced by system water and debris. And so all of the cogen really knows is hey, this tank is hot, or it's half of it's hot, or now it's 3/4 of it's hot, or the whole thing is hot. And so let's say it's cool, it kicks on, the unit heats up, we dump water into here, So that's all the cogen knows. From there, there's a couple of ways we can use the heat. We can use it for domestic water. In this case, it's stage 1 of DHW. Stage 1 of DHW, we circulate water to and from the storage tanks to this tank. Now, this tank isn't just like a big buffer tank. It's got a coil in it. So a lot of times people will call it reverse indirect because the boiler water, other than being in the coil, is actually on the volume side. And so this case, the hot cogen water, probably about 185 degrees, and then you have a coil where the domestic water is being sent up through, it's being heated, and dumps it back into the tank. So I had to put this is one of the kind of little diagrams I did, put a little package together for the utilities for a couple of the sites for them to, follow the sequence, and then we just leave it with the site so people would be able to follow it. And so that's stage 1. Now try to go to stage 2 here. Down. Stage 2, really, the only difference is that everything's already doing what it's doing, except now in parallel to the support from the cogen, in parallel, the water heaters are now satisfying the domestic. And then let's say if the domestic load is satisfied, trying to maximize that runtime, what you're doing then is you're then injecting it into the heating loop, trying to maximize that runtime. And so something as small as that, they have these carbon footprint calculators online. The EPA have these. So one of them came up with a unit as that small was the equivalent reduction of 14 cars or 10 homes being removed. So there's a bunch of technologies out there. Cogen, I think that we've kind of seen our day for natural gas units for the most part here in Massachusetts, but if you're looking at any of the biogas, I think that there's a big opportunity. I'm not sure if anyone's familiar with, I believe it's Lowell has a fairly large plant, or UNH. They have their plant that's supplied by the transfer or the waste management in, I believe, Rochester, New Hampshire. So there's a way that we can use these gases and produce heat as well as electricity. It seems to be the most efficient shuffle. I'm wondering whether I should jump into the second half before the food, or yeah. Let's take a look. Oh, yeah, nice. All right. Well, at least for the folks that are remote, we're going to take a break, and we'll be back in just a bit. All right. Can you hear me, George? All right, perfect. All right, so to end this off, just I think that you can see the agenda here, but it's important to look at through different technologies for electrification and for the decarbonization efforts that we have. And there's obviously VRF, and part of what I'm have here in this presentation, you can tell it's a bit biased towards water, but there's a lot of solutions out there with the electrification, decarbonization that as we're removing boilers and all these different items, that there are substitutes where we'll continue to be making pump selections, heat exchanger selections. So a lot of the stuff in this class, I don't see at any point it becoming obsolete. Pumps, heat exchangers, and just fluid water in general. Water is an excellent heat transfer medium, and I don't really see any long-term solution for replacing it.
Just at the moment, you're just doing the instructor sharing. You want to probably reshield.
Oh, which one is it? Okay, so it's different than what you see up here?
Yeah, I can see it.
Okay. Is it this one? How about this?
Yep.
Oh, cool. Thanks, George. All right, so just a quick rundown. Talk a little bit about electrification, introduction to Galetti. Galetti's one of our products. That's the air to water. Really just going to use it as an example. You can apply it to a lot of the different folks, a lot of other folks who are out there, but just something I'm a bit more familiar with. So that's why we'll talk about it a bit. There we go. So this map, just as we all know, the coastlines are typically going to be at the forefront of the energy codes, project electrification, even attempts at gas bans, whether it's Cambridge or Arlington or Boston or all of these different sorts of places. Well, you won't see that in other portions of the country. Just like we were talking earlier about how there's some of the challenges of our region being at the forefront is trying to apply what we have here for technologies and trying to learn a little bit from what they're doing in Europe. So for Boston, in Massachusetts here, we have BERDO. So it's a Building Energy Reporting and Disclosure Ordinance. It's outside of compliance, there are fines up to $1,000 a day. Don't think of it as it's always $1,000 a day. There's plenty of ways around it. That maybe they're not the most simplified, but for instance, if somebody has multiple properties, they may be able to have their own schedule for decarbonization, where they could have something tailored to their portfolio, or you can buy credits to be able to offset some of your emissions. Ultimately, what it is there's a schedule starting this next year that, based upon the square footage and based upon the primary use of that building, that there are ceilings essentially to what they have as kilograms of carbon per square foot. And so that's how you're going to see it for the carbon intensity. So this link down here that I put 1021, if anyone's ever worked with like a Map Geo or GIS maps, where you see all the different properties, you click on them, gives them a property card. Similar to that, except it's really their emissions card, I guess you'd say. And so you could select it, and you can look at the map. You see green's conforming, gray's not, maybe it hasn't reported. You can select a building. You can say, okay, that building, that's a healthcare building or an apartment building, and it's X. And I've used it a couple times for projects where people are trying to figure out what the expectations are for certain areas, and I can pull it up and then pull up BERDO and say, okay, they have to be conforming 3 years, or they are conforming now. But I put 1021, so the link is active. So when you get this, you can click it and you can use it. But just note that link, that Boston link, was last updated in October of 21. So it's been a couple of years. So it's a decent reference, but I'm sure that quite a bit of it may be dated. Cambridge has their version of it. Obviously far less of a fine, but I'm sure things will step up. Beyond Massachusetts, the ESG I just have on there, but beyond Massachusetts, environmental, social, governance, these sorts of goals they're a top priority now, probably more than ever for any publicly traded company. So if you have a client that's a publicly traded company, there's a lot of investors now that try to be conscious investors, and so sometimes that it may even be a driver. The point of this slide is just the same as prior when we're talking about heat exchangers, we're talking about pumps. We have to know what the driver is. So if you have a customer that is looking to do some of these things, okay, now what is it for? Is it for fine avoidance? Is it for there's plenty of different drivers. Just making sure that as we put a proposal together of how to solve it, that we're addressing it appropriately. And I think that we've got a bit of an advantage here at FIA. I think that than a lot of other folks, or really anyone else in the industry, given that we're on both sides. We for many years were gas suppliers on the gas equipment supplying. We now have entire full electrification products from supporting really any project size. So when you have something where you just want to run it by, we're going to try to be technology agnostic. That's what we're going to say. Whatever you want to try to achieve, maybe we do a hybrid approach, maybe we go all heat pump, maybe we do boilers, maybe there's some sort of staging. So just making sure that it's clear what we're trying to achieve, because if not, I've had plenty of projects where we've looked at it 5 or 6 different ways before really then it comes out about what the client really wanted, and then back to square one again. So just making sure that we understand the driver of our customers. In Massachusetts, like I was saying in the break, at least to the folks here in this classroom, there are significant incentives. And some technologies, they may not have incentives, just prescriptive incentives out there. They might go down the custom approach. but the funding is very, very, very significant. And the plan, so the plan is just under 5 billion for the next 3 years. And when you go through that plan, it breaks down in different categories. And when it does, it actually compares the next 3 years in funding, not to the last 3 years, but actually to the last 11 years of funding. It just give you an idea of how much this funding really is. It's unbelievable. So unbelievable, actually, that when I was calculating now, they're missing like $490 million in the plan. So maybe that'll be added later. But I put the link to it so you see the draft plan if you want. You can click it. I'm curious if anyone finds that Easter egg. So just on refrigerants, this is actually, I think, another thing that we, in the first class, we were talking about and kind of made me think that this should be put into a slide is to understand where we're going with a lot of these technologies and products is kind of to understand where we've been. And at least with refrigerants, there have been different things that have been motivators and reasons we've moved away from different things and where we're going. So I like this. This is actually a slide from Danfoss. I thought that it was great, and without spending a ton of time on it, but just kind of giving a breakdown, is that in the 30s and 50s, that's when there's really the takeoff of the chlorofluorocarbons, that essentially the chlorine molecule that then people realized that how it interacted with the ozone, that we were damaging the ozone. So then we said, okay, well, we're going to shift away from that. And that's where they came out with the HCFCs, which just meant that it still had a chlorine molecule, but it had a double bonded carbon, which just meant that it wasn't going to last as long in the atmosphere. It had a bit of a shorter half-life. And so they really didn't solve the problem yet until they got to HFCs, and they said, okay, there's no more concern about the ozone depletion. But then people started realizing, okay, well, what about global warming potential? So global warming potential then became the thing. And so now that we're shifting away from HFCs, which is really what in Massachusetts is actually quite recent, bless you. So for instance, this year, with chillers, there was what's called as 310 CMR 7.76, which says that they were banning certain hydrofluorocarbons, one of them being 410A for chillers. So, and the only reason that I kind of went down the rabbit hole in this one is because we have a heat pump that produces hot water and cold water. It's a heat pump chiller, and that if I use that product for heating only, it's fine. You can use it. But if I want to use that same product for cooling for that same building, then that refrigerant would be banned, which was pretty fascinating. So I went down the rabbit hole with Emily Lamb at the Mass DEP, and I mean, I see where they're coming from. That there are reasonable substitutes for it as a chiller for 410A, but in terms of a cold climate, it's a great performing refrigerant. So now everybody's making the shift. So you have a lot of the 410A easy swap out for the most part is 454B, very, very similar. So a lot of people have made that shift, and that's where we start getting into the HFOs. So now we're at the days of back to naturals and HFOs. But it's going to continue to evolve from there. So if anyone's paying attention to like what's going on with refrigerants in Europe, the conversation is on PFAS. So I'm sure it's been a hot topic among, drinking water and the forever chemical, but PFAS is, I believe, like 2,000 different chemicals are identified as PFAS. And some of those identified as PFAS are actually the refrigerants that are blends. So a lot of HFOs, pretty much all of them are blends. And so there's 2 of them that make up just about all of the different blends. It's like 1, 2, 3, 4, like YF, and I'm sure somebody could comment on it. But either way, there are some countries in Europe that are now already banning the HFOs that we shifted to, like even a 454B, because of the PFAS. So kind of brings us full circle, like we were saying before, though, but now with refrigerants. So naturals. So then with naturals, you say, okay, well, what is Europe doing? I mean, that's usually an easy way to figure out where we're going with a lot of things is what Europe's doing. So in Europe, they're using R290. So R290 for a cold climate like this, if you're using it for heating, it's pure propane. So the purest form of propane doesn't smell anything like that, but it's a great refrigerant. I mean, you'll see all different brands have products that are producing 170, 180 degree, leaving water temperatures, units operating down to minus 20 Fahrenheit or even greater, very high COPs. So that's where it appears things will be going. And if I had to put a bet on it, I'd say in the next 2 years, we'll have progress here in the States where a lot of these things will be lifted. But earlier when I mentioned that ASHRAE 15 that creates the standards for the safe handling of the refrigerants, right now, so the standard 15.2, there is an addendum E that went out at the last winter ASHRAE conference. And what they did is they put a group of folks together to start studying the work that's been done in Europe and how safe are these products. We understand they're already doing it, but let's check for ourselves. So I think they created a process that was approved this spring. They received funding in just recent, like past probably 2 months. If I had to guess, I'd say that if not this this winter conference, I would expect that there should be a position when the next standard meeting is, and then from there, if the charge limits increased, which I skipped that. So the current charge limit in the United States for like R290, which is probably going to be the major refrigerant, is probably the equivalent of 2 Bic lighters. It's like 150 grams. It's not going to do much. They're looking to increase the charge limit to 4,900 grams, like half of your propane tank on your grill. And they could probably break it up even by circuits. But we're a bit behind Europe in that sense. So if that's approved, then it'll go to UL. UL will then have to do their own studies, and then from there likely be the EPA. I think things are going to be a quick flip at the EPA. The reason being is the GWP of R290, I believe, is 3. And I think that a big indicator that kind of flagged a lot of this to my attention last year and thought that this is definitely going to be the case sooner than we think was when the DOE actually funded Copeland $2.5 million towards R290 compressor development for heat pumps. So the fact that the DOE did that with Copeland last year, and then granted how everything else is progressing, it really only leaves for reasonably low ambient, once you factor in the PFAS, is R32 and 290. And even R32, we're still in the 600s for GWP. So technology's trying to adjust as quickly as it can, but policy is changing. It's changing very fast. So just a quick plug on our product and what our experience with our products are. So we have represent a modular heat pump chiller brand that it's called Galletti, based out of Italy. They have 650 employees. They've about 500,000 square feet of production space spread over 11 plants. So their offering is obviously much bigger than what we have here in the States. We offer just one series of modular heat pump chillers. They offer an array of geothermal, many different units. So this is the one product type that we offer. We offer it in 2 different refrigerants, but to give you an idea, 14 ton to 54 ton for cooling, and 200 MBH to 778 MBH. And these units can be ganged together as many as you'd like. Now, I guess we can skip the whole EVI thing, but unit operates down to -4 degrees, produces 149 degree Fahrenheit, water temperature down to about 12 degrees. And then by the time you get to -4 degrees, you get to that about 131 outlet temp. I'm going to skip past some of this. Okay. This just kind of gives you a visual. and this is pretty standard in the industry, that they're going to, if they don't achieve this, they're going to be pretty darn close. But um, I bring this up because just thinking of the limitations of some of the new technology, if let's say you have a leaving water temperature at 149, we have to be conscious if we're doing any selections and trying to determine, is this a system that can operate on low temperatures? And even if you have, let's say, an older system, and you'd say, well, this can't support the design day conditions with 100, 145, 149, or even 31 degrees, 131. There are applications where what we're doing is we're doing kind of a staged approach where we operate the unit as often as we can, and then unless you upgrade your coils or your existing heat emitters, then what you would do is just have a changeover temperature, similar to, I think, what George and we were talking about earlier. Residentially, you have commonly in Massachusetts. So it just shows the 149 down to about 12 degrees, and then the -4 producing 131. Units are pretty efficient. So I've done some cost comparisons on some units that are heat only versus heating and cool, these heating and cooling units. And I'm actually starting to use some of these units even on my domestic projects, because the efficiency, being able to run, the efficiencies are typically beating the units that are hitting the heating only. And then even if we don't factor the cooling, typically the unit is at a better price than a unit that does heating only. So this just gives also, I'm sorry, trying to zoom in here for best I can. So can you guys see that? Yeah, okay, good. Just showing that these are the standard water temperatures where, as mentioned before, that AHRI 550, 590 that they developed for chiller systems. There's been some tailoring to it, obviously, with this we're improving our heating. But if you look at our cooling charts here, there would be better. So a lot of the details are pulled from 550, 590, but there is no standard at this time. So that's why you have everybody saying that they're in compliance with 550, 590. This is just showing the operating range for the outlet water temperature for the cooling mode, produced down at 23 degrees. Obviously, must be have a glycol system at that point. So some of the benefits that you're going to see throughout the industry of products similar to this is that you'll have different load set point control. So you'll have an onboard control that'll be cascading multiple units, kicking them on and off, trying to hit a set point. You might have a primary pump control where, like I think George was talking about when we were talking about primary, secondary, about sending a speed signal to the primary pump to be able to maintain that delta. You'll see in a lot of these heat pump systems that there'll be a lot of buffer tanks incorporated. A lot of that is so that you don't see a drastic swing in temperature. If we're able to adjust the speed and we're able to match the load, then just like a boiler, we're going to maximize our efficiency. We're going to prevent recycling. So that's the function of it. It's very similar to a boiler, if you're familiar with that function. Remote connectivity, obviously nowadays everything is connected. In Boston and around Boston, many of these units are going to have, like this has, is there's certain set times where you may cap out your blower speed, your fan speed, to minimize any sort of noise. I know Cambridge is very strict about that. But the units, they all have their onboard controllers, and in this case, these units would control 6 based off their onboard control, and after that, every 6 would be grouped together. But I think that's pretty standard. In this case, just wanted to show that, just like boilers and everything out there, there's these packages for the near boiler piping. In this case, the near heat pump piping, where you can select 2-pipe, 4-pipe systems and get these assemblies. That right there, I just wanted to throw in a picture of. It includes the pump, and the pump is the E80X. And just to touch on the E80X again, so that unit is the IE5 NEMA 4 unit, and we're excited to be putting that with these heat pump chillers. we'll be able to directly receive that signal. Let's skip past some of these control items. Most of the units out there in the industry are going to use very similar controls. So they should have all of these same items. Let's do a quick schematic. So enough with that product specific. So here, this just shows that hybrid approach. So once again, we've got it so that this is showing a two pipe system, and this is with connected to our heating circuit for with the backup boilers. So we have our heat exchanger, getting our cold water from a return line, preheating it, or possibly even just satisfying the load up to a given temperature. And then if we do need additional capacity, then we would just be able to stage on the remaining unit. So that can be done by set points in the units, the heat pump chillers, or it could be third-party control, or you could also have it as simple as just programmed onto a boiler of when to kick on or kick off in terms of outdoor air temperature. Just going to show here is this is a domestic application. So put a buffer tank on it. If you just have a single unit, a buffer tank's not necessary because you can start factoring in the volume of the storage tank. But one thing you'll notice is that in this drawing is that we've got a heat exchanger isolating these circuits, just like the last one we were isolating it. Now, if the entire system was glycoled, that wouldn't be necessary. So I just added that, assuming that we're not glycoling the whole entire system. Many of these manufacturers, they won't require that you glycol the outdoor circuit, and they'll have these different ways of having pipes wrapped or preheated, but doesn't seem to make a lot of sense. We believe at least our position for any of the domestic heat pump systems where you have a hydronic circuit, that it's best to just glycol that circuit. In this case, it's a domestic application, so obviously we would have to isolate that. But it also brings up the point of there are some units out there that, let's say that they've got a double wall heat exchanger and they're rated for potable water. Well, that's great. Let's say if we're in the South where you're heating the water in the unit and you're sending it directly to a storage tank. But if let's say you're up here up north and you're glycoling that circuit, then you have a double wall heat exchanger. It's got an air gap. You're reducing your heat, the ability to transfer heat, right? The thicker the plate is, if there's an air gap's an insulator. All of those things will make it so that that heat pump will then be knocked down in efficiency. And then on top of that, you're going to add another heat exchanger anyways to isolate the glycol circuit. So now you got heat exchanger at the glycol circuit, heat exchanger at the unit, could be double wall. Next thing you know, we have 4 walls to satisfy something that could have been a single wall, and depending on the pressure, a single wall or double wall, and also depending on the state. So factoring those in, and all this is just showing is that if we were to have a unit circulate to and from a storage tank, that it would then feed an electric backup, and I like to call that like a peak shaver. Also, just if you satisfy the base load with your storage tank, and then if the water is coming out and it's not up to set point, that backup or electric peak shaver might kick on. A lot of times what I will do in the designs is I'll have it so that that second unit in series, the one right before the mixing valve, that backup electric, I'll have that set point maybe 5 to 10 degrees less than the storage tank, so that as it does come out, the only time that element's going to be kicking on, for the most part, will primarily just be when, as a thermal loss from the tank exceeds that differential. But if you have a big enough differential and it's storing, feeding at warm enough temperature, you can minimize that to minimize it pretty well. So some technologies out there are other heat pump options. You'll see a lot of people, we see a lot of promotions sometimes for CO2 units. Now, CO2 units, what that would require us to do is it'd be a single pass. So let me talk a little bit about this unit. Is like a traditional unit that puts hot water in, pulls cold water out, and it takes multiple passes, probably increasing 5, 10 degrees, 20 degrees, depending on what the temperature was and the flow rate. But ultimately, it's passing multiple times before it gets that storage tank up to temperature. Now, if you have a CO2 unit, CO2 units, they require a large differential on their water side, very large differential. And so that's why a lot of times you'll see promotions for, okay, we can store at 180 degrees. The reason is because, you know, if you have a return water temperature that exceeds even 70 degrees, a lot of times that'll actually kick off the CO2 units. They have a go off on a high inlet water temperature alarm. So just keep that in mind, depending on what refrigerant may impact your piping design and your entire system sequence. And there are other things to CO2 to discuss, but with regards to piping, that would be the big consideration. You know, a lot of folks out there, what they're going to have, just like what we have, is that you have specific conditions. Let's say you're trying to offer something to a customer, and you want to tailor some of these conditions for some modeling. We can enter those sorts of things and provide printouts. So this is just, as I'm clicking through, it's just going to show. Also provide schedules. I think this is really just great for the service folks, but you can click on a model and you can pull components out, spin them, and it'll give part numbers. And it's really nice if you want to become familiar with how the product works. Here's some of the outputs. So the next we're going to get into is one of the more recent, one of the sites that that we have that's going in with one of these Galetti products. And these summaries were very helpful in the modeling for it. So these outputs that I'm showing you right now. So it's part of we're going to end a bit early today, but the last few slides here I just have are on the site example. So this property, they're currently conforming to the next year's Birdo. The issue is that as of, I believe it's 2030, they would be out of compliance. So it's not anything that they're concerned about now. But the thing is that they had a failed chiller. And they said, okay, well, if I have a failed chiller and I replace that chiller, and then it's pretty costly, and then, you know, in X amount of years, I'm then going to be paying potentially a fine of X amount per day because I replaced that chiller with, you know, with the same type I had there before. So ultimately, what we did is we worked with National Grid. So different people at the utilities. So like at Eversource, you have Ryan Willingham, you have Kevin Silvera at National Grid. All of these folks, they work with a lot of the new technologies and work on the incentives. So what we did is we went there with the customer. We looked at what they had. They needed a lot of new things. So they needed new pumps, expansion tanks, air separators, a lot of stuff that were dated in the system. And so we put the quote together of all of these different components. And actually, I'll price breakdown in a moment. So those are all the items that we replaced. They left the existing boilers for now. So in this example site, or this site that we're going through with, is that the heating mode is activated at 68 degrees. And then from there, what we do is we produce 90-degree water to the system. So they have these water source heat pump, you know, a bunch of the Whaling units. And so it's a big apartment building. So it's a low temp system. And so at 68 degrees, we send it 90 degrees, and then 140 degrees at 0 degrees. And so we just mimicked their existing reset curve. And obviously the unit stops at 68. And this was really interesting. So we were talking earlier during the lunch break about how residentially, if you doing a full electric conversion, that you know, people are being required to disconnect some of their existing boilers in some cases for some funding residentially, but commercially, fascinating enough, was we were able to leave all the boilers there and still receive the $1. So at 10 degrees out, we're able to kick on the boilers, and they're not kicking on the boilers because the heat pump can't keep up with it. They're kicking on the boilers because there is a point where, you know, the COP drops off to enough, and the efficiency of the electricity on the grid doesn't make a lot of sense. So it's really not a carbon reduction. And then on top of that, the customer is going to pay 3 times as much when you think of the cost of natural gas compared to, you know, a COP of 2 or something along those lines. So doing a breakdown of it, the project, you know, the equipment, the contractor's quote to the building owner was just over $1 million. The incentive was $890,000, sorry. Yeah, $890,000. And the cost of the project to the building owner will be less than the cost of just the chiller alone. So it's fascinating. I mean, the funding is unbelievable. Now, you'll notice though, it is in two, it's in two parts. And the reason for that is that, like I mentioned about there not being a standard for heat pump chillers, and that's why they have to go through the custom approach. What they want to make sure of is the utility wants to make sure of if they're incentivizing something that they're truly going to see these efficiencies that they're promised. With us, we're not concerned about it because the testing for our product was done in Italy, and they already have a standard there, and it's much more strict by Eurovent. And we know that they're not going to try to inflate our numbers, or that could slap their hand in Europe, which is their bigger market. So they said, okay, we'll hold 178,000 back until the end of one heating season. And then if everything proves out to being what's published, you get the remainder. But that's significant. This project, this is not low income housing. So if it were low income housing, it could potentially be 100% of the project. Which is what happened with a lot of the even cogen projects. So a lot of funding out there, and their concern was the compliance fees, having to buy the new equipment in the next 5 years, plus the cost of current chiller. So sometimes the numbers seem a bit excessive, but that's all right. Let's see. I guess this would be a good time. Is there anything anybody wants to talk a little bit more about, or
Say in compliance with 555-90, and there's no standard of testing. I'm assuming you're saying Galletti does their own study per your standard. Is that
yes, I'll just repeat it. So the question was, is that if there isn't a if 555-90 doesn't apply to this Galletti product, for instance, that what does Galletti do? So Galletti over in Europe, what they have is they have Eurovent. And so they have their own climatic chamber, the environmental chamber that they have to have certified to the standards of Eurovent, because people can manipulate things by the size of the chamber, the capacity of the chamber. So their Eurovent developed a standard quite some time ago that I think 555-90 will be kind of, they'll take 555-90, but then they're going to incorporate some of the Eurovent items, and then they're going to call it something else and probably leave 555-90 for the chillers. But yeah, so it's Eurovent. That's what they're certified to in Europe. Yeah. One of the other things too is that these units are really based on airflow. And so depending how many units that you gang together can influence your pre-cooled or preheated air. So one of the things that isn't in 555-90 that will be in the standard that will apply to the heat pump portion will be factoring in clearances. So a lot of folks right now might be able to get away with things by saying that you can stack these units right side by side, and you can, that's fine. But the thing is that if people are going to publish that, then what they also have to do is test their equipment doing that and show it. And then if you want to do that, then you have to publish the D rate. If you just want to publish that best number, then you have to provide the appropriate clearances.
attenuating walls?
Yeah, right. Yeah. So there's a lot of smoke and mirrors in the industry around a lot of the new products. So it's important to do our homework. That's our responsibility. But anything else? All right. Well, everyone that's remote, George, are we sending the golf shirts and the certificates, system sizer? Okay. So we'll just use the shipping address that when they sign up. Okay. All right, excellent. Then everybody here, we've got the certificates and the golf shirts. Oh, we'll ship the golf shirts as well. Okay.
Have you guys been emailing out the slides, or are they posted on the?
So I think we've been, as people have been reaching out, we've been saying to them, but what we'll do is we'll have like a Dropbox link. Okay. We'll send a recording of all of these, also all of the slides, and then I think, do we also have a digital version of the binder for the most part?
Yes, the TEH. We
Yeah.
thought that was happening, we realized it wasn't, it was just responding to individual requests, so.
Yeah.
David had kind of gathered everything, we just gotta kind of clean up the presentation tonight to put it as part of.
All right, thanks, everybody.